All right, folks, welcome back. I just want to say a few more things about the extended zone versus the reduced zone in 2 dimensions. So from one point of view, we could always just use the extended zone scheme. Okay, so that is always valid. We could always just use it. We would then make use of the entire K-plane in 2 dimensions, and we would sort of tile this plane into the various Brillouin zones. So the first zone, the second zone, third zone. We will soon see how that plane gets tiled into these different zones. And it's quite elaborate. These higher order zones are quite almost fractal-like, but they always add up to the same area of 2 pi over a squared. All the various Brillouin zones are of the same area, and in that sense, they fill out the entire K-plane. Okay, so we would look at that, and whenever we crossed one of those boundaries between 2 neighboring Brillouin zones, then we know we get this energy jump, this energy gap. Right, so this is why it's still important to draw into this K-plane the various Brillouin zones, BZs, because the boundaries between 2 of them tell us where the energy jumps discontinuously. All right, so we could use that scheme. Now, alternatively, there is an advantage to the reduced zone scheme. This is why we're introducing it in the first place, right? So there's got to be some kind of advantage. Because, you know, in the end, it does take some work to construct it. The extended zone scheme is maybe the more immediately obvious, the more immediate scheme. And then the reduced zone scheme is derived from the extended zone scheme. So there's a little bit of work involved there. But the advantage really is that we see everything very compactly in our field of view, right? We don't have to scan the entire K-plane. We see everything nicely in that one area of that one small area of the K-plane, the reciprocal lattice plane. So everything happens sort of in one compact area, and we see the various states organized into the different bands now within the reduced zone. Okay, so we do get now different bands stacking on top of one another in the reduced zone. So that is sort of the visual advantage of this reduced zone scheme. It is just easier to comprehend what's going on, but both are equally valid. Okay, so now that I've said that much, let's see how we go from the extended to the reduced zone scheme in 2 dimensions. And here we're going to use a simple square lattice in 2 dimensions. And we get this kind of sort of reciprocal space where in here we have our first Brillouin zone from minus pi over a to pi over a, pi over a to minus pi over a. So that nice square here. And then we saw that the second Brillouin zone is given by these triangles here. There's 4 of them. It's not very hard to see that the 4 triangles add up to the same area. Okay, so now let's take a look at this lower triangle there. It falls outside of the reduced zone, and I want to sort of shift it into the reduced zone. So what do I have to do? Well, I'm going to use one of the reciprocal lattice vectors to shift it. And here it's clear that we have to use the B2 from before. Okay, the reciprocal lattice vector that points up. Okay, and so I'm going to use this area and then shift it by this reciprocal lattice vector, which I'm allowed to do according to the Bloch theorem. Okay, so what happens? Well, then it appears there. So it's gone down here and it now reappears up here. Okay, so we can now, why stop there? Now let's tackle the next triangle. Okay, we want to shift that into the reduced zone as well. And it's clear here we're going to use the reciprocal lattice vector that's pointing down, right? and it will shift this corner here of the triangle, this vertex, to the origin, and these two vertices down to here, right? And so there's no surprise we're going to get that triangle down here now after the shift. Okay, and so we'll handle the two side triangles in the same manner. This one here on the right, we're going to shift to the left by a reciprocal lattice vector of minus b1, and then this one here, we're going to shift to the right using the reciprocal lattice vector plus b1. Okay, and so when we do that, we get basically this. And so here, we've basically taken the second Brillouin zone and shifted it into the reduced zone, lying right on top of the first Brillouin zone. Okay. So then I get sort of the second Brillouin zone in the reduced zone this way. Okay. So anything that happens in the second Brillouin zone of the extended zone scheme can now be shifted in and is now the second band within the reduced zone. Okay, so hope that was somewhat helpful. I got some questions on that point, so I just wanted to address that here. Okay, so now shifting gears just a little bit, and this is also in response to a question that I received in office hours. And the question had to do with how valid is really the free electron model that we use to draw these circles of constant energy in reciprocal space. And the answer is, obviously, it's not going to be valid, especially when we get close to one of those bisecting lines, those Bragg planes. Okay, so what I want to draw your attention to is a particular paper that I found interesting here, and that is that appeared in the European Journal of Physics. Okay, you can see it here in 2017, so not long ago, not that long ago. And I want to sort of first discuss this picture up here in the upper left corner. So we see here that we have the first Brillouin zone here in yellow and the second Brillouin zone here in blue. Okay, and so, and then there's also the third and fourth and fifth. They're in different colors. But we've drawn here a circle of constant energy. And it almost looks like maybe that circle encloses half of the area in the first Brillouin zone, let's say. Okay, so this would be maybe appropriate here for a monovalent metal, where we said that the first band is exactly half filled. So that means, right, that we need to fill up an area that's half the area of the first Brillouin zone in the extended zone scheme. And so we could say that everything within that black circle in a monovalent metal would be filled, and everything outside of that black circle would be empty, right? Because we have an occupancy. We have electrons here, only enough electrons to fill half of the first band. Okay, and therefore we need an area that's half of the first Brillouin zone in area. So this would be a circle, and since we're far away from any of these boundaries, we could say that the circle is approximately going to be a circle even if we turn on the lattice potential, because we're still far from the boundaries and nothing much changes there. But now let's get closer to the boundaries and let's look at this top right picture. So now we've extended the circle out. This is now a circle of larger energy, and so if we had more electrons, we'd have to go out further in energy to fill up, to basically accommodate all of those electrons. And so here's a particular circle that just touches the boundaries of the first Brillouin zone. Now this would be for the free electron. We're just drawing a circle. But since it touches the boundaries, that can no longer be true when we introduce the lattice, right? The lattice perturbation, or the perturbing lattice potential. The weakly periodic potential of the lattice is another way of saying it. So as soon as we turn on the lattice, then this circle can no longer remain a circle, but what it does is it looks maybe more like that. So now we're down here, okay? We have to distort the circle. So what we do is we come here, this is still sort of circular, and then we touch the boundary at right angles. Okay, we stay here, and we sort of always approach the boundary at right angles there. Okay, so this circle would now be sort of broken up into these 4 segments in this way of visualizing it. Okay, so that would still, though, be a circle that the original circle was less in area compared to the first Brillouin zone. So now let's extend the circle more, okay, to the point where we're now at the divalent metal, where we know that in the free electron picture, we need a circle of an area that's equivalent to the first Brillouin zone, right? And so clearly now that circle has to be expanded a little bit more. Okay, and so before we were just drawing a circle here in the lecture, okay, but we were crossing all kinds of, Bragg planes or bisecting lines, if you will. And so it's clear now that that circle cannot remain a circle in the presence of a lattice. That gets distorted as soon as we approach one of these bisecting lines. And so what we see happen is something more like this picture here. Okay? So this used to be a circle, but now we get some kind of effect like that, only pushed out a bit. So this black line here corresponding to this black line here. And we always approach the bisecting line in a perpendicular fashion. Now, of course, things now extend into the second Brillouin zone as well, and that's here shown in white. Okay, and again, we would see that part of the second Brillouin zone is occupied, okay, namely whatever is sort of inside here of that yellow line, these 4 yellow lines, that would be occupied with electrons, those states. And everything that sort of falls into this corner here, into these corners, would be unoccupied. Okay, so the basic argument, the thrust of the argument from before still applies and still holds. It's just that the shape is just a little bit different from the single circle in the presence of the lattice. And so that's the second clarification I wanted to bring in at this point.